Hello, and welcome back to part 2 of the fourth test in the terrain engine. Today I will be finishing up the validation process, as well as the LOD selection, the transitioning rules, and the overall visibility redesign. Before we begin though, let's go ahead and take a quick look at what we will be getting into today. So picking up where we left off is with the validate triangle mesh. And to do this, it's relatively straightforward. You are going to loop through every triangle that gets extracted, and from these triangles, you're going to calculate the surface normal. That's done like this. You simply just cross two of the edges from a common starting point. That'll give you the surface normal of the triangle. Then with this surface normal, you can take the magnitude squared, and if it has some surface area, then this triangle is generate. You do run into the possibility where the triangles generated have no surface area, and these are degenerate triangles, and they're removed now. I believe I touched a little bit on this in the third test, but I'm not too sure. However, this is the validation process. After the triangle has been validated, we then swap the y and z of the surface normal to move it into the proper world space coordinate system. So really the main part of what we're doing is trying to reuse as many vertices as possible. So because of this, each triangle reuses its own vertex, but we still need to remap that into a way that it can be used for the renderer. So what I do is find the voxel index that was extracted with, and then check a map and see if the index for the voxel has currently been encountered before. If it hasn't, then we're going to store the current mesh vertex index. So we start at 0, and then anytime we get a new vertex index, we increment it by 1. This allows us to keep only unique vertices, and then at the end, regardless of whether or not this was a new voxel vertex, we just put the index into a list, and then this index list is used by the element buffer in OpenGL to render the smaller list of triangle vertices. One thing I would like to mention though is with the addition to the normal mesh vertices, a second check also has to be made to see whether or not the vertices were along the face of the cube. This is part of the changes to the modified marching cubes that I showed. However, even that code has changed a little bit now. Essentially, what you do is this table maps all the possible transition states and their corners. If a vertex or a cell, in this case, that is being extracted happens to be at a corner of two faces, then it has to be handled a little differently than if it was just on a normal face. So you do the check first to see if there was a shared corner count, and if there wasn't, we just do the check to see which face, if any, this sample happened to be on. Going back to the validation process now, we simply check if the vertex happens to be on a shared face but not a shared corner. If so, its index is recorded now. If it's on a shared corner, we have to do a few things. Because each face has two corners, each face has this primary extremal indice variable, and I'll show all these later. But essentially what these do is they hold the combinations of the vertices for each face pairing. So 0, 1, 1, 2, 2, 3, and 3, 1. Or sorry, 3, 0. Then by using these combinations, and they're gotten like this, we can check whether or not the corner was the minimum or maximum complementary corner, and if the face was the positive or negative axis. So when I say complementary corner, what I mean is that the X face needs to check against its Z axis on the corner. And the same consideration needs to be made for the Z face with the X corners. The main reason why this is the pairs are stored for their complement. So the X face stores its Z shared indices for the vertices. Likewise, the C's share their X's. So later when we see the transition code, it should make a bit more sense as to why the X face shifts with the Z extreme and the Z extreme shifts with the X face. And after we have looped through every triangle, and well, one thing I forgot to mention is at the end here, because we're trying to calculate vertex normals, we want to add in every triangle influence to the vertex. So that surface normal we calculated earlier can now be added into this vertex normal's or to the contribution of this vertex normal. Then at the end of every triangle, we go through and do this transform to put all of the actually normalized vertex normals into the mesh itself. Then after we're done with the primary mesh, we do a check to see if there should be a transition mesh. If there is a level of detail, there will be a transition mesh. Just some pre-calculations. And similar to the primary meshes, we are just looping through every extracted triangle, but in this case we have a little bit extra work we need to do. And this work is just to figure out which of the faces of the primary mesh are we pulling out its transition mesh. One thing that does need to be noted here is this transition chord and complementary chord. These just simply switch on the Z-axis and determine whether or not the Z bit is present. If it is, it just determines what state we're dealing with. If we want the complementary chord of the Z, it'll be X. If it is X, it'll just return Z. These are used to index the vectors to get their X or Z components. But we can now look at the extraction process, and there's no validation done here. This shouldn't really say validated, it should say added. But we just assume that every transition triangle is fine. Similar to the primary mesh, we do have to check if this is on not necessarily a shared face, but if it's on the half resolution face, or if it's on the side of the transition cube that meets the lower of the two level of detail blocks. And we handle this in here. So we do the check to see if this is an extremal vertex by simply saying, is this sample or is this vertex, does it lie in the first or in the last cell? If it does, it's extreme, and we need to not shift it now, but only if there is a shared corner that is also being transitioned. If this is just a regular half resolution face, we can just shift it now, because the only time that they will be visible, these will always be transitioned. So we just store it now. This is a bit of a deviation from how the paper says to deal with it, but it's something I've found that works a bit better and probably does reduce the GPU overhead of not having to deal with extra bits across every vertex sample for what is arguably a very small portion of them. And then, like with the primary meshes, we just add in our tracking information, our indices, our vertices, our indices, our normals. Although the normals, right now, they're not correct. I'm taking a look at these with the texturing and shading part of the transvoxel paper. So this will be readdressed, but it was put in there simply to make sure that the data is all lined up right and can be accessed. I'm not going to really get into the details because it is definitely going to change, but essentially after all the extraction is done, the nodes are just put into an update queue for the render thread to grab them. And so now we will actually go look at the renderer's side of the handoff though. And if you're familiar with multi-threaded code, you'll see why this is in fact going to change. The physics engine actually has been set up to where it should be able to be handled much more easily, to say the least. Less blocking, again, if you're familiar with multi-threaded code. But that is all besides the point, because what we are interested in is right here. So essentially we just run through each of the nodes that are given to us and then hash their positions, and then based on their position we put them into the grid. When we are doing this process, we also go ahead and make the meshes for them now, and I'll go ahead and show that. It's pretty standard OpenGL code. This is combining the vertices and the normals into one buffer, and I believe it's also interleaving them. And then this is the OpenGL upload code. Very, very standard. This bind format enable is just a wrapper around some other GL functions that you essentially always call together. So whenever you are creating an attribute binding, you're usually also going to format and just enable it, so it's all done here. As well as you're also usually going to just complete the vertex buffer once you're done, and you're going to reuse this information. So it just reduces on the number of copy-paste bugs. And then the process for creating transition meshes is also very similar, where we find the face that we're working on, and then we combine our data. Again, the normals are kind of bonked right now, but it'll be fixed. And then we do the normal GL stuff, bind format enable, complete the vertex buffer, and then we just return. Return to the next face until we're done. So now I'm going to go to the visibility code, but I'm going to talk about the actual system itself. So the visibility system has been completely redesigned essentially. Now, actually this is wrong. Actually, all of this is wrong. Sorry about that. So essentially now what happens is at the beginning, the previously rendered cells, or the cells that were sent to the renderer, are removed, and every node that is possible to be visible has its current level of detail set to invisible. And it's this invisible flag that we're going to use to make sure that we don't render anything that is visible. This is first done by creating the visibility set, and this is just, actually I think I said it right there, it's a vector of U32s, so it's simply the list of hashes that are visible. That is generated inside of this call invisible cells function. And this simply loops through every node and does a check to see if it's visible. And if it's not visible, it puts it into a set that's rejected. And if it is visible, it puts it into a set that is accepted, but this set is also returned, so it's named result. It's also at this time that once it's determined to be visible, we go ahead and set its level of detail. And then anything that was rejected has the possibility to be accepted later on. So we also need to loop through and go ahead and remove any false negatives. After we remove the false negatives, we have to detransition, or do a detransition check. And this is because of how the actual engine, I guess, itself works, is every frame it's doing this check to make sure that things states, so the state between the LOD of one neighbor and another lines up. Once it's determined to be invisible at this stage, it can never get to those later stages to be checked and then determine that it needs to detransition there. So that is done now. And so this is that transition corner combination table coming back into play again. And this is because we need to handle the corner transitions separately than the face transitions. This is again because faces can transition without corners, but corners cannot transition without faces. So to detransition shared corners, we are going to get that combination code and we are going to loop through every count. Almost always, it's going to give you a 1. Very seldom, and I don't even think this is possible, but it's in there for completion. Very seldom does it ever give 2. And this, I think, is due to an artifact of how the LOD rule and selection that I'll show in a bit manipulates the edges and how detail levels are set. So because of this, I think it is possible. Well, I mean, it is. It's very rare. But you can transition on 3 faces, which gives you 2 corners. If that happens, we unfortunately need to be able to account for it. However, though, we're usually just going to run this loop once. And like before, you'll extract out your X face, your Z face, your X extreme, and your Z extreme. And then depending on these combinations, you're going to go ahead and detransition the corner combinations. And this will make more sense once I show the detransition function, but essentially, whenever you're detransitioning, you're always just resetting the vertices. So we supply it with which vertices we want to reset, where those vertices are, so the entire triangle vertex list. And then we want to tell it which buffer in OpenGL are we dealing with. And then using that we can, and this works for the non-shared corners as well, but you can just take whichever indices you have that you need to detransition, whichever mesh you need to use, and then whichever buffer you need to use. So you can just keep doing this over and over and transition whatever, or detransition in this case, whatever vertices are necessary. Then heading back up to that function, after we detransition the corners, we head back down and we detransition any active face. So this just simply loops through the face or the node, each face of the node, and try and find if there's a currently transitioning face. There can be, as I said, up to 3 currently transitioning faces, so we need to find them all and detransition them the same way. We just give the vertices, the vertex locations, and then the buffer to it. And then at the end, we just want to clear out the part of the bit code that contains which of the which of the faces of the cube we're transitioning, because none of them are anymore. However, we also want to store whatever the previous level of detail was. However, after this is done, and we have gone through every rejected hash, we return the list of accepted hashes, and after that, I believe, yes, we'll send it to the set detail levels, and this does the LOD rule. So essentially, the LOD rule just says that you cannot move more than 1 level of detail at a time. And this isn't a hard code thing, it's just something that I put in place for the engine. The reason for this is how the triangulations work. If you go from, say, LOD 0 to LOD 2, you're going to miss LOD 1, and you're going to have cracks and seams in the world. So you have to do some manipulation of that first pass to make sure that things line up properly. The actual rule itself is pretty simple. What you're going to do is, because the grid is index based and 0, 0 is the bottom corner of the world, and the NN cell is the top corner of the world. By having the indexes of the grid containers, the actual container and memory, line up with the representation of where each terrain node is. When we say we want grid position 2, that is the same as saying we want terrain node 2. Because of this, if we start at the lowest possible hash and then continue to work our way up, we only ever go north and east on the grid. Therefore, we only ever need to retroactively check our west and south neighbors. So this is done by first looping through each neighbor of the current node that is visible, and if that node's neighbor is on the grid, then we check its level of detail. And we want to record the lowest of ourself and our neighbor, because at the end, if there is a difference of more than 1, we need to do that correction. And that correction is just a simple recursive check. So you'll go through each neighbor, and I don't believe this ever really goes too deep, but you will check the west and the south neighbor, and if their LOD is greater than ours or the current node by more than 1, and it's not invisible, then we need to do the same process where we're going to update our neighbor. We're going to update our neighbor, and we are going to check their neighbors as well. And we continue all the way down until everything has been satisfied, at which point we return back to here. And then when this is done, we return back to here. And then now this is the third pass that is done, and this is where we actually do the detransition and transition detection in the terrain. So basically what we're trying to do here is determine the changes in states between levels of detail and nodes with their neighbors. What I mean by this is, imagine in one frame, 2 nodes that are neighboring one another are the same level of detail. But then in the next frame, one node goes to a level of detail that is 1 higher. There is now a transition that must be detected between these two for this frame only, because in the next frame, if this condition is still true, we don't want to transition again because then we'll start creating gaps in the mesh, but we don't also want to detransition because we'll just need to retransition again and we're going to waste GPU time. So what we do is first just see if there was a detailed change. If there was, we go ahead and restore the entire mesh, similar to if the mesh was deemed to be invisible, I believe right here. Very similar process. Once we have determined if the LOD has changed or not, we go ahead and hash the X and Z coordinates, and then we're going to check each of the neighbors. To check each of the neighbors, we're going to pull together the combination of the states. So we can determine if we should detransition, or if the situation is set for a detransition when the current level of detail is less than or equal to its neighbor. This isn't indicative that we are going to be detransitioning, but what it really means is that we do have the potential to, because we make the check to see if we previously had a transition. This will likewise with the transition to make sure we don't transition more than once, make sure we don't detransition more than once. It also helps to solidify this kind of check. However, if we have had a detransition between these two neighbors, we detransition the face, again with the vertices, the vertex locations, and then the buffer. Sorry, these are the vertices and these are the vertex locations. And then after we detransition the face, we go ahead and check if there was a shared corner, at which time we detransition if there was, and then we remove the transition bit from the face. Sorry, we remove the face bit, which is the transition, from the transitioning faces variable. This variable, and I'll show this later, but it stores the previous level of detail as well as the current states of the faces in their transitioning status. So if the detransition failed, we want to now check for a transition, which is very simple. If we have the potential for a transition and we didn't previously have the transition, we go ahead and transition now. And to transition the face, it's pretty similar, and I'll go into this in a bit more detail in a second. But in addition to the vertex locations, the vertices themselves, and the buffer, we also supply where in voxel space this node was, the current level of detail that we are transitioning with, and then what face we want to transition on. This tells us which way we need to shift the vertices. Then once we determine that the transition happens, we go ahead and OR the transitioning faces with the face bit, and similar to this turning it off, this just turns it on. And then we set that transition flag to true. So this is the, I guess, complement to detransitioning shared corners. This is how you transition shared corners. Again, it's very similar. You give it the locations, give it the actual vertices, give it the buffer, and then the extra data that it's looking for. Here, though, we do a few more transitions because the extremal vertices for the transition meshes, they get shifted twice. The reason we need to do this is, if you remember when we created or validated these, anything that was an extremal corner was previously shifted already. Then anything that was a corner got left for this moment. So what that means is that because we are transitioning on an X and a Z face, those corners need to receive their old Z or X, I suppose, transition, as well as their complementary X or Z transition. For the primary meshes, it's a bit simpler though. We just do the complementary combinations, the X face, get the Z extreme, and then we transition those indices with the X face. Similar for the Z face, we get the X extreme, and then we transition those indices with the Z face. So now I'm going to show the actual transition and detransition functions, and we'll begin with the detransition because it's a bit simpler. To detransition, we just simply loop through every index that we gave it and find the original voxel sample. From that sample, we're going to scale it down into world space and then move it into world space by essentially flipping the Z around. So we add in, I want to say this is the maximum size of the world and then negated, and then this is added to the Z component of every world space triangle vertex. And this has the effect of, if in voxel space your sample was 0, 0, it moves it to 0, negative max Z. But detransitioning, you're simply just resetting those vertices back to their original positions. To transition, we go ahead and pull out the original sample, and then we find pretty much what sample number this was. So if there is, say, 32 total possible samples, but this was the 5th cube, then we're dealing with, I think, like 150 cells already. So we need to remove all those cells and get it back to just that 0 to number of cell range. Once we determine that range here in the centered chord, we go ahead and calculate how much this particular vertex should be shifted. I have no idea where this function is. There it is. And then this is the function that Eric describes in the paper. This, I will admit, I believe because of how it works, there is a lot of unnecessary shifting that occurs because many of those samples they return 0. I still think it's better to use this even if we return 0 for most things, because we need some efficient way to handle both the extreme cases, and that's really what this is handling. If it's a minimum, it moves it inward. Well, I guess outward, and if it's a maximum, it moves it inward. However, after you do this for every visible cell, you have then successfully built the entire visibility for that frame, and then you can go ahead and run through. This isn't the visibility set. This was that list of original meshes or terrain nodes that the visibility set was created from. We're going to go ahead and go through each of these nodes now, and we're going to update the high nibble with the current level of detail, but we're going to preserve the transition faces. So it's kind of the reverse of what we were doing here. And then after you've done the bookkeeping, go ahead and anything that was visible, now you send it to the renderer for rendering. Go ahead and say that we don't need to build anymore. And then this is just timing stuff that I was playing with. That does remind me, in the previous video I had to cut a little part because there's a issue with the timer. It way underestimated the extraction. So it said it happened in something like a few nanoseconds, and that's just not right. It is fast, but it's not nanoseconds fast. However, to comment on this, in release mode, the visibility does, for like a 100 or 10 by 10 grid, the visibility builds in about 0.02 milliseconds. However, aside from the actual structs and helper classes themselves, the only other thing that really needs to be shown is the render code. If I can find it. Here it is. So this is all debug stuff, simply to override the colors to, I think it's used to determine, the level of detail where it's at. But to actually just render the stuff, you just pull the mesh for the current level of detail. You want to bind the vertex array and then set your shader information. This isn't actually working right now. Again, I'm working on the texturing and triplanar projection. And then you draw your elements. And then similar for the transitions, anytime you have an active transition, so if the transition face bit is there, you do the same thing, bind your VOA, get your indices, and draw them. These are just black right now because they're being worked on, and it also helps to visually see where the transitions are happening so you can verify that there's no cracks or anything in the mesh. So in my haste, I just realized that I forgot to go over something. And that's the actual thrust I'm calling, which is pretty important, which is this. Go ahead and show this now. But essentially, you're doing a collision test against a plane and a box, and you can do that by projecting that box onto the plane. When you project a box down to a plane, at most it can have half of its overall length be projected down onto that plane. So all we're really doing is checking to make sure that it's not completely negative, or that there is at least some part of the box that is on the positive side of the plane. If we cannot find that, then we return false. I'm sorry, I misspoke a little. What happens is if we find the condition where the box is projected past the positive side of the plane, that's when we return false. If this condition is never satisfied after the loop ends, we return true. Now, the actual planes themselves are generated from the world space matrix of the camera, and this is the, I believe this is the inverse of the camera. I'm going to actually find that now. All right, I found it. So yes, it is the inverse of the view matrix. However, you use the inverse of the view matrix itself, the focal length, aspect ratio, and desired near and far planes. And then this whole function creates a polyhedron, but as far as the planes themselves, they are generated like this. However, now with all that being said, I do believe that should be everything. So now I will show the supporting code and the demonstration. But as far as the core of the code is concerned, I believe that's it. I'll go ahead and put up some pictures now and some little synopses, I suppose, of the what it's doing, what this structure is for, how it works, and then I will show a demonstration and fly through of the currently extracted terrain with its performance. So I'm going to go ahead and show the actual transition and detransition functions now, and I'll go ahead and start with detransition because it's much simpler. And with that, it should be the end of the fourth test, the LOD and transition rendering for the terrain engine. Thank you very much, and I will see you with test 5, the texturing and shading with the triplanar projection. And with that,